Bizarre. Cool, we're good to go. So first of all, apologies, I'm frightfully annoying in the mornings, and I've had 2 cups of coffee already, as Guy can attest to. So, cool. It's really awesome to have you all here today. So, thank you so much for coming to the Manchester Community Summit. I love coming up here and talking. So, my name is Mike Dukes. I'll introduce myself in a minute. But yeah, first of all, it's like my absolute pleasure to be sharing this stage with the very awesome Guy Templeton from Skyscanner. Skyscanner are doing some really, really cool stuff on AWS. So we consider them like a really cutting edge partner of ours and customer of ours as well, because the stuff that they're doing, we can all learn from, and we can just see that kind of trend and go from today. So what we'll cover today is we'll talk about really how Skyscanner have built a resilient architecture using Kubernetes, and how that was made possible with EC2 spots as well. And with that, they got considerable savings. So I'll let Guy introduce himself, if we can up his mic if possible.
My name's Guy Templeton. I'm a principal software engineer at Skyscanner in our production platform tribe, mainly focused on shared container platforms, also on continuous deployment these days, but also a co-chair of SIG autoscaling in the Kubernetes world. So that's the other hat I wear.
Cool stuff. So he's very involved in KubeCon and stuff. So if you ever want to get the ticket, annoy him.
I'm not.
I'm Mike Dukes. I'm from AWS, and I look after what we call the flexible compute business. I'll talk about what I mean by that very shortly, and that will just give a bit of an introduction to some of the services and technologies that Guy will talk about too. I just want to quickly talk about part of the organization that I'm in at AWS. So I'm part of what we call the specialist organization, and we exist for 2 reasons. One is to kind of deep dive on individual services, and the second one is to give feedback to the services. So a lot of the services that we create at AWS are all based on feedback, all new feature improvements, and we love to hear. We always love to hear from customers. So if you have any kind of feedback, be it, hey, I'm using the service like this, we'd love to hear about it, or things that you want to do to improve the service, it's really, really vital to us. So please come and have a conversation anytime. The reason that I mention this is as AWS customers, you have access to that organization and those specialists. All you need to do is talk to your account team. We have specialists in all the different various areas, like be it containers, serverless, networking, be it databases, be it analytics. There's all those specialists available to you. So please feel free to reach out to your account teams if you ever need to deep dive with that as well. Cool, so the agenda, I will be very, very quick today because I want to hand the stage over to Guy for the majority of the session. But I'll just give you a quick overview and recap of what Spot is, what's the best practices, and what's some use cases. And then for part 2, we'll go on to Skyscanner's journey, how they looked at this cell-based architecture, what they did with the containers platform from beginning to end, and kind of some great additional benefits that they saw from it. So feel free to have a seat if you want for 2 minutes. Perfect. Cool. So the first thing I like to talk about when I talk about what I do is flexibility in the cloud. And what do I actually mean by that? So there's some key principles to think about when we talk about the cloud. There's an old school mentality is that we need to take what we did on data centers and shift it over to what we do on the cloud. And actually with being flexible, you get loads of advantages. And what I mean by that is basically, first of all, using architectural best practices. So thinking about architecture in the right way based on the cloud. This means using specific AWS services and the instance types that are good for your workload. And that effectively, you're getting towards the mentality of running as optimally and efficiently in the cloud. There's loads of technical advantages to doing this. So the first one, and Guy will allude to this a bit later, that you naturally become more highly available and resilient by being flexible in the cloud. So if you think about that, you make use of different availability zones, that's adding high availability. If you think about how you're architecting in a certain way, you're also building resilience to your applications as well. And the whole point is we want the cloud to be elastic, right? We want it to grow when we want to use it and shrink when we don't. And we actually find that a lot of our customers that go and work in this mentality are able to innovate. So they're able to innovate with the latest technologies, whether that's newer instance types, whether that's different tech in that sense, or save that money that they use in their purchase and spend it elsewhere. Like obviously Gen AI is a big buzz at the minute. So like there we see a lot of new projects happening from a consequence of good optimization. There's loads of benefits to this, right? So first of all, for cost in the cloud, you only pay for what you use. So the more efficient you are, the more optimal you are, you will actually only pay for what you use. So it's good to get in that mindset. The second kind of element as well is that you can start leveraging purchase options. So spot and flexibility go really, really hand in hand, but there are lots of different purchase options as well that we can make use of. And sustainability is becoming a really big topic in cloud compute as well. And this is like the key pillar that we launched in reInvent a few years ago, is that actually to work more sustainably in the cloud, it all starts about being as optimal as you can. So in terms of what I particularly look after and kind of the themes of the flexibility in the compute space, we're talking about some of the EC2 core stuff. We're talking about Graviton, which is obviously ARM-based chipsets that you can use in the cloud. It's a very efficient and optimal way to use compute. We're talking about EC2 autoscaling, so growing when you need to, shrinking when you don't. EC2 Spot will be the theme of today. Compute Optimizer we also look into, and Carpenter as well. So I'll be running a Carpenter workshop, so if you're interested in what that is, it's all about Kubernetes optimization and scaling. It's a different tool that AWS has open sourced, and I'm working with a certain community at the minute to make that more community-based and focused as well. But I'll be running a workshop this afternoon. Would love you to be there if you want to learn more about that. Cool. So very, very quickly, I'm sure everyone knows like the basic purchase options, but if I was to start with an on-demand instance, that is effectively, I need to compute there and then. It's really good for spiky, stateful workloads. And that is the key word that I'm using here, stateful, okay? You want to retain state on-demand instances, it's quite good. We've then obviously got savings plans, and savings plans very much is you know exactly what you're going to be using over a period, whether that's 1 or 3 years, and you can get a significant discount off the on-demand price. And finally, Spot. So what Spot is effectively, we are taking spare capacity that lies on AWS, we're provisioning instances from it, and effectively that can give you savings up to 90%. Now the key thing with using Spot is that it has to be a fault-tolerant, flexible, and stateless workload. They are the really, really key things. If you don't have that, don't use Spot, because by the nature of what it is, it won't work for you. So I always like to kind of show, there was just one point to that end as well that I forgot to miss off, but purchase options aren't exclusive, right? So if you want to use a bit of on-demand, if you want to use a bit of savings plans, if you want to use a bit of Spot, that absolutely works well. We typically see some people use a baseline of savings plans and on-demand, and then kind of the excess on Spot as well. So they're not mutually exclusive. When I talk about spare capacity in the cloud, I like to start with like a visualization of a blueprint of instances. So when we did this talk at the summit, we actually had 600 instance types. We now have 650 instance types as AWS. But the point of this blueprint is to think about how spare capacity works in the cloud. So on this blueprint, you can see that I've got the M6G series. They've got 8 sizes with them. I've got the C6i series. They've got another 8 sizes with them. And then you've got the C6G series. They've got another 8 sizes to them too. And if you think about what the cloud actually is, EC2 stands for Elastic Cloud Compute. So for us to be truly elastic, for us to be able to offer that elasticity to customers, we have to have spare capacity. And the fact that we have over 600 instance types, actually over 650 instance types now, means that there's a lot of places to leverage that spare capacity from. So let me show an example back to my blueprint. Here, I can see that I've got the C6i 12x large instances. So I can say that the white squares on this diagram actually represent the spare capacity. We call this a spare capacity pool. And when we provision an instance for Spot, we're taking from that spare capacity pool and we're provisioning an instance. And that is what a Spot instance is. That gives us a great discount, and that effectively allows us to use spare capacity in the cloud. And one of the key things when using Spot and this is why I love to do this intro before kind of handing over to someone that has actually used it, is diversification and flexibility. Think that spare capacity is across all the different instance types, different availability zones. It can be time flexible, it can be region flexible. So if you are making use of spare capacity, it's really key to use as many instance types as you can, to be availability zone flexible, to be even region flexible if you're going to go all in on Spot, and so for some workloads and use cases, be time flexible too. And to finally, just to kind of give a bit of an overview of Spot, yes, it's interruptible. That's what spare capacity is, so you can be interrupted, which is why it's so important to consider the right applications for Spot workloads, okay? So think that they need to be fault tolerant. Can my application handle being interrupted? Can it be flexible across different instance types? Can it be loosely coupled? And can it be stateless? There are also, this typically equates to these types of workloads with Spot. So containers and Spot is pretty much hand in hand. It's a great use case nearly most times because typically the nature of what a container is, you provision it, you throw it away, it's immutable, it goes really, really hand in hand with Spot. And there's also some other things as well. So web services, we've got HPC and batch. If we want to grow and shrink and do a lot of compute, that's the place to kind of do it. CI/CD, we see a lot of people use it in test environments or pipelines or some other areas there too. A lot of customers use Spot in production for these workloads, and that's a kind of key thing to take away before Guy takes over. There's loads of service integration, so there's obviously the container services out of the box, you get that. Carpenter, which is an open source tool, also builds Spot best practices into it, so it makes it really, really super easy to adopt Spot. There's also autoscaling, which has a lot of features in, and EMR too, which is typically that's where I'll start with customers. If they say, I'm using containers and I want to use Spot, good place to start. Are you using EMR, are you using autoscaling groups? It's also a really good place to put Spot in as well. Big misconception on pricing is that people still think that Spot is based on bidding. It's not at all. We used to have a mechanism with AWS back when Spot was first launched. It's no longer bidding. The price is set by AWS. The reason that we did this is to make it really easy, okay? So you don't have to worry about being outbid. You don't have to worry about managing the price of your individual Spot instances. The point is you focus on the wider discount that you get by being as flexible as you can across all the different instance types. And finally, if there's one thing to kind of learn from just what I've talked about, is if you're using Spot, make sure you're diverse and flexible. Think about, can I use different instance types? Can I use different sizes? Am I running this workload across availability zones? And for the occasional customer that's going all in, am I running it across regions as well? That's kind of an optional extra. You don't necessarily need if you're running small amounts, but just think about spare capacity. Spot is spare capacity. The more flexible you are, the more you can get across. Cool, that's me. I think you're mic'd up.
Think so.
Cool, so we'll switch this one.
See? Yep. Awesome. Thank you very much. So yeah, I'm going to cover a bit of Skyscanner's journey into the cloud and using containers at scale, sort of some of the challenges that we started having with our initial architectures, how we designed a resilient architecture, and then how we used Spot to enable that, and some of the gotchas and best practices as well that we've found with running Kubernetes on top of Spot in AWS. So what is Skyscanner, for those who aren't familiar? Its mission is to lead the transformation to modern and sustainable travel, with 75 million monthly active users, over 1,200 travel providers, and 24 billion origin destination partner combinations. So there's a lot of data crunching involved in that, as you can imagine, particularly when you support things like country-based search. So in terms of a cloud-native journey, what problems we faced, technology choices we enabled us, why we use Spot, and the trade-offs. So Skyscanner's growth and scale in the cloud has been pretty fast. I joined Skyscanner just over 8 years ago now. When I joined, I think we were around 5 million users a month by the end, but by the end of 2019, we were getting close to 100 million. Obviously then something happened to put a bit of a damper on travel. But when you expand that fast, things that were once solid start to not scale, have problems, etc., break apart at the seams. And when I joined Skyscanner, we were still running in 4 data centers using VMs, and we just started looking at this thing called the cloud and moving some workloads into AWS, having a look at this containerization Docker thing, and we very quickly decided that was the future. So we started designing what would a shared platform for our service owners, deploying new applications into the cloud look like as a first thing before we started doing any lift and shifts. So we started off by going, oh, okay, so service teams probably shouldn't need to own an ECS cluster each themselves. That feels suboptimal, it's distracting them. We don't fully, as a company, know all the best practices in the cloud yet, so why should each service team need to figure this out? So we'll provide a shared ECS cluster per region for our users. And so we can see here that we've got an ELB per service. This ECS cluster is spread across multiple AZs. So we get some of the benefits of bin packing on this shared cluster. We built some tooling to allow improved bin packing as well, and abstract some of the things away. But eventually we decided to revisit ECS as the choice. Like when we'd initially chosen ECS, we sort of looked at this Kubernetes thing, I think it was about 1.2, went AWS, like we have a good relationship with them, we think that might be the future, not this Kubernetes open source thing, we don't know what that will do. Eventually we were talking to enough vendors going, oh, have you got a solution for this for ECS? And they were going, no, we've got a k8s thing, we might do ECS later. So it was becoming a bit of a pain. Kubernetes had got the developer mindshare by this point as well, so we decided to join the hipsters and move to Kubernetes. And we initially copied the same architecture. We had one Kubernetes cluster shared across all our services. It was a multi-AZ cluster in each region, but we got a benefit here. We managed to lose those ELBs that we had per service, and now we just had a single ELB per cluster. That might not seem like such a win, but when you've got 400 to 600 services per region, depending on the region, losing that $20 a month per ELB, it quickly adds up. But number of problems with this. Multi-AZ clusters, for those who have tried to run them with Kubernetes, stateful workloads quickly become a pain because you need to make sure that you're scaling the right thing to ensure that your EBS volume is where your pod is. And also, like, we had problems with noisy neighbors here. And also, if we had an outage of that cluster, that entire region was down. So we needed to shift all of our traffic across. And that meant customer journeys were lost. People had to start their searches again, etc. So it wasn't a great experience. And we were hitting scaling problems as well. At this point, Kubernetes' scaling story wasn't as good as it is now. So we went, okay, cool, we'll just spin up a second cluster. And we'll have a second DLB in front of that cluster, and we'll deploy some different services to that, and new services that are wanting to migrate from ECS onto that cluster. That leads to a number of problems. So despite now having 2 clusters, we still hadn't improved the reliability of our regions. If we had an outage in cluster 2 and service A relies on that service in cluster 2, you still have a regional outage. And equally, if service A goes down and it's the, say, flight search homepage, you still have a regional outage because it's only deployed to that cluster. So each deploy at this point of whether it was config or service was, at its most granular, still a region level deploy, which could impact our travelers. And we really didn't want that. Equally, services also needed to know where their dependencies lived. So part of the URL for these services was effectively the cluster name. So if I was service foo trying to talk to service bar, I needed to know whether it lived in cluster 1 or cluster 2. So if a service was wanting to move between clusters, it needed to go and talk to all of its consumers, go, please update the URL you're calling us on before it could delete its old version. And also noisy neighbors were still a problem at this point in that there was no shuffle sharding here. There was every cluster in the different regions had the same set of services. So yeah, noisy neighbours still a problem. Spanning clusters across AZs caused us a number of problems, and the other points that I mentioned. So all of these problems meant that we revisited our architectural choices again. And around this time, AWS had started publishing a lot of material and talks on their cell-based architectures, so how they deliver resilient platforms for customers. So there was stuff in the solutions library, reInvent talks at this point, of how they ensure that they are able to roll out updates to services that we all consume as users of AWS, while reducing the potential blast radius and impact on customers. So this provided with us with a bit of a vision to aim for. So we started looking at what does a cell-based architecture that is achievable for Skyscanner at the time look like. So the core tenets for us were, we didn't want a single point of failure, whether that was us rolling out updates to infrastructure or service owners rolling out updates to their service, whether it was config, a new container image, a new version of a service, etc. And we didn't want to use that old ECS model of a load balancer for every service to get some cost savings. So this was sort of the architecture that we alighted on. So there's a number of changes here. So this is a map of a single region. Here you can see that each cluster no longer spans multiple AZs. It's scoped to a single AZ. And services are deployed into multiple clusters here within a region. So we can see that service A is deployed to cluster A1 and cluster B1. So it's now deployed to two separate AZs. So we're following the outlines of the AWS sort of fault zones. And that means that an outage of an AZ, we can still theoretically be able to serve traffic. An outage of a cluster, we can still serve traffic, and potentially a bad service deploy, as long as it's only deploying to a single cluster at a time and has requisite metrics checks, etc., to detect that bad deploy, we can tolerate as well. So if we have that same failure mode that we saw before of a failure of a single cluster, now we can be resilient to that, in that we can just route traffic away from that cluster, and I'll sort of cover on the technologies we use to do that. So we did it in phases as well. I mentioned that we didn't want a single point of failure. We did initially have a single point of failure, which was an NLB in front of all of these clusters. That wasn't so much a concern from an AWS point of view, in that it was a multi-AZ, etc., so it was tolerant to that. However, if we pushed out bad deploys of the NLB, that became a problem. So we did then start splitting out our NLBs, so we were tolerant even to bad config updates to our NLBs. So we started, one of the benefits also that this brought when we started migrating our services was this broke assumptions by our developers. So we started looking at what other changes could we bring in at the time we were making this such a major change to our architecture that previously we'd been scared of making. And we also, like I think a lot of customers who made the journey into the cloud at the time we did, the AWS tooling around managing organizations wasn't great at the time. So we just went, oh, we'll have one big cluster, goes across all the regions, and we'll just move everything into that account. And that, unsurprisingly, results in a lot of hairy technical debt. So instead, by this time, the tooling had improved for managing organizations, spinning up new AWS accounts, making sure that they looked the same across different accounts, mapping in OIDC, etc. So this enabled us to design these AWS accounts around the new clusters. Previously, we'd had to sort of mash our Kubernetes clusters into the IP space that we had available around everything else that we'd thrown in to these VPCs. In these accounts, we were able to do it entirely from scratch and go, okay, so what does an ideal VPC setup look like for us? There are a number of challenges, though, with this cellular setup that we were looking at. So unavoidable is the increase in base infrastructure costs. We're going from 2 clusters per region to, actually in our case, 6 production clusters, but also some traffic routing clusters, so actually 9 clusters. So we've got 9 control planes now. We need observability tooling in each of them. We need some DNS stuff. We need NLBs in front of them. All of the add-ons, I think we're up to about 30 that we install into every given cluster. All of the add-ons that actually provide a workable environment for our service owners. And also the wastage of services. So a service is now deployed into up to 6 clusters in a region. They might not tune their HPA optimally, so they might not scale down as much as they want. So there's amount of unavoidable overhead as well with this cellular setup. But it did make future big migrations possible. So at the time we moved to the cellular architecture, we were using a tool called k8s, Kubernetes Operations. It's an open source community-driven tool to build our clusters on AWS. That has a number of downsides, which includes that we had to manage our control plane. That was running on EC2 instances, but we moved to EKS as part of this migration as well. And that provided a number of savings for us in that we didn't have to take care of as much of those instances, but also we moved from very beefy instances because of our large clusters to paying, I think, $70-ish a month per control plane. And we are looking at moving from cluster to scalar to Carpenter in the future, because we can make these changes in a single cluster, evaluate what the impact is, whilst not risking our traveler experience. So in terms of the technologies that enabled us to do this, the key one is service meshes. Hands up who is playing with service meshes, using service meshes, at least familiar with service meshes and what they do? Okay, cool. I'll give a bit of a quick overview, but the service mesh choice allowed us to build in network level resilience. So this is the key enabling technology for us in building a cellular architecture that's able to route around failure. So it allows us to fail over traffic within an AZ, where either we have a bad cluster, an AZ problem, a bad service deploy, or a config update, etc. So we can fail over first within an AZ where that's possible, because no one likes cross-AZ traffic costs, but then we can do cross-AZ if we need to as well. So what you can see here is our setup where we have a service called trying to talk to another service, and we send traffic via an NLB, via an Istio default gateway into our service. However, if this service starts failing, we can the service mesh is instead aware of this other instance of the service living in a different cluster, and will route around that. It will also, in our case, keep on retrying occasionally this server pod, and if it becomes healthy again without any intervention, then it will start routing traffic to it again by preference. So service mesh is effectively responsible in our setup for being aware of these services across where the pods of a service live across multiple clusters, the health of those pods, so it will monitor response codes, latencies, etc. It'll provide us with observability for that as well. So a key part of our observability for service owners is provided by the service mesh to see what response codes they're getting, what latency their service is giving, if particular clusters are a problem, etc. So this allows them to run quite granular metrics checks when they're doing a deploy as well. So at the time we did this, Istio was in version 1.4. It hadn't got native multi-cluster support, so we did have to roll our own multi-cluster setup. And we also created a component that we call the drain operator to allow us to perform some more safe deploys, particularly updates of clusters. So this is sort of what we can see. This is traffic distribution per cluster across a given region. So what we can see here is at the beginning of this time slice, we have equal traffic distribution across our 6 clusters. And then this green cluster at the bottom, we drain traffic away from it. So this means that microservices that receive incoming requests in that cluster, they're not getting any requests whilst this is drained, we can perform maintenance on this cluster in this window. So if that's a Kubernetes version update, rolling some nodes because we need to patch an AMI, or updating, say, the DNS configuration in that cluster. We can then run some tests at the end of this window, slowly restore traffic back in. We can continue monitoring for service metrics, or if service owners manually alert us that there's a problem at this point. And then in this case, we have then almost immediately applied a different update to that cluster. Here you can see it's a far shorter one, so I'm assuming it's something quicker like patching an image in the cluster. And then again, we restore traffic back in. We can also manually use this technology to drain traffic out of a cluster. So I've sort of covered some of those problems. So why did we look at Spot to enable this? And one of the things people occasionally get confused by is Spot for production workloads, and unsurprisingly, people have hot takes on Twitter. This is in response to an incident that happened, not for Skyscanner, a few months ago, but people responding, oh, you should never use them for critical infrastructure. It's unreal that an architect in DevOps would allow a production system to migrate to Spot instances. I'm still employed somehow, so. And key services should never be used to Spot instances. I'm going to say all of those people are wrong. Shockingly, people on the internet are wrong. So we were seeing ever increasing infrastructure costs. We were getting more traffic. We had the increased overhead of this cellular architecture. Even the move to Kubernetes over ECS had resulted in more platform overhead. And we still wanted the cost savings of scaling elastically with traveler demand. So Mike mentioned the other potential purchase options for EC2, so looking at savings plans, etc., reserved instances at the time. Those weren't great because we have a very elastic demand profile. And also the move from bid-based pricing to smooth pricing of Spot removed a lot of that uncertainty of going, oh, what if the price spikes above the on-demand price? Will it all just disappear, etc. So we proved out our use of Spot in our sandbox accounts. So these were our effectively dev playgrounds. We saw that actually we weren't seeing a lot of Spot reclamation. So we weren't seeing our service owners going, oh, I tried to validate it in sandbox account, but I couldn't because you kept on having no demand there. And we iteratively built our confidence as a business. So the first Black Friday after we'd moved to Spot for our production workloads, we actually moved back to on-demand a week before. In most of our clusters, watched to see what the Spot reclamation was like in some nodes that we'd kept. And then moved back to Spot afterwards. The year after, we didn't do that. We just we had a runbook in case we had problems, but we just managed to use Spot entirely over Black Friday, which is obviously not only Amazon.com's biggest event, but at the time, but also other retailers that make heavy use of AWS were making use of instances around that time. So that's why we were sort of scared. And also AWS over time started adding new instance placement strategies. So Mike mentioned there's a number of best practices built into AWS services. So auto-scaling groups have a placement strategy where you can basically say, I want any one of these instances, so that flexibility Mike touched on. But when you ask for a Spot instance, here's how I think you should choose that, whether it's the lowest price or the best capacity, or price capacity optimized, where there's an algorithm on AWS's side to say, here's the one where there's a balance of best price, but also less likely to get reclaimed. And most of the tooling now supports that. So the other benefits here, of course, were for our service owners, we started effectively having a chaos monkey running in our accounts for free. So some service owners who were used to their services running on a VM for 6 months at a time, then patching it manually with a new Vagrant image, they'd sort of built that basis for running their services into their thinking. The fact that we were starting to use Spot was sort of going, no, those instances will go away at some point. You need to be prepared for that. Whether it's an AWS issue, whether it's Spot reclamation, whether it's just us making a bad config update and we tear down an ASD by accident and your pods all get migrated to somewhere else. And it was another step in treating our infra as cattle, not pet. So we didn't want to continue going onto boxes and manually patching things. We wanted to be sure that any time a Spot instance went away, the new instance that came up would be able to run containers successfully, serve Traveler workload, etc. And it exposed some assumptions and bugs in workloads that weren't expecting their clients to go away, or weren't expecting the services they were calling to go away at any point. They were always expecting their requests to fail, or where it was calls that weren't idempotent. So as Mike touched on, diversification has been key here. So for Skyscanner in a single region, we make use of nearly 250 different capacity pools. Those are, as Mike mentioned, a combination of instance family, size, and AZ. Not all instance families make sense for us. So we're not using all of those 650 because some of those expensive ones with GPUs, weirdly enough, they're still expensive even under Spot savings. And we also, but at the moment, we also need to keep track of new capacity pools as they become available. So new instance types, new instance families, I think C7Is are now available as of the last week. New AZs, if they spin up and we want to expand clusters into them. That's a bit of toil currently for Skyscanner. Also Graviton, there are some challenges here with Kubernetes at the moment. So Skyscanner aren't currently making use of Graviton in Kubernetes. That's because we need multi-arc images, need to make the cluster clear where workloads can run on Graviton nodes. We also want some observability. So we want to have advanced warning of issues or risks with Spot, monitor for rebalance recommendations, terminations, shifts in usage of different families. So this is a graph you can see where we are mapping what instance types we are using across a week. So we can see some patterns like this blue one, we get periods where we get absolutely no CPU capacity in it at all, and then suddenly we get a load of capacity in it. So we want to have some monitoring on that. I'm going to quickly burst through the trade-offs. So we do still have lots of duplication though, even for low-scale services. Spot helps us to offset this. But the figure on the talk title is a bit of a misnomer because actually what Spot has done here is enabled us to build this architecture that does have overhead in a cost-efficient way. And we also need to give cost allocation. However, this diverse range of instances can mean wide range in price of a given unit of compute for our service owners. We have some tools that we use to monitor it. So Spot placement score that we use to sort of look at what Spot instances might be able to give us capacity, placement strategies, Spot instance advisor. There are third-party offerings. I have not made use of them. However, Spot can be used for production business-critical workloads, enabling new architectures that we would not have been able to deliver without the savings that Spot brings us. And it's not without challenges, though. It requires thought on how to deal with Spot terminations, making sure that your workloads are able to tolerate the things that Mike was talking about, that they're fault tolerant, that they're able to resume their work, etc. And also potential disaster strategies. If Spot goes away, what are you going to do? Don't just assume it will never go away. So to come back to the hot takes, and this is what actually those hot takes were in response to. Those Spot instances get reclaimed and not being prepared for this. This is the problem. Like if you assume that they will never have an issue, you're going to have a problem when eventually it does. There is some further reading and watching on cellular architectures, etc. if you want to watch it, but yeah.
Nice.
Thank you.
Thank you so much, Guy. Yeah, so it's super awesome to have Guy like come and tell us an actual real story where we actually hear it being used. I just really wanted to point to this link actually. So if you want to adopt Spot on any workloads or anything like this, EC2spotworkshops.com is a free thing that we use. We actually use it for all of our workshops as well. So be it whether you're on ECS, EKS, Carpenter, EMR, autoscaling groups, you can go and do the workshops on your own account, or you can come and join an event with us where we can just go and run through them. And that's us. If you want to add me on LinkedIn, I haven't give Guys out because I don't want him to get really annoyed. But you feel free to add me on LinkedIn. If you get a chance to just do the survey, that would be really appreciative for us as well. Like, it just really, really helps us. And that's it, I promise, Phil. All done.
Oh, so questions? I'm sure there will be questions. Yes.
Hi, thanks very much for that talk, Guy. Very interesting. I was wondering what role deployment played in all of this, because I work with organisations where the way they deploy the software becomes a major barrier to be able to do some of the big architectural changes that you were describing there. So have you got some secret sauce there around how you do your deployment of your software?
So we have an in-house tool that we built over the years called Slingshot. It was initially built for ECS deployments to do effectively blue-green metrics-driven metrics check-driven deployments onto ECS. We've extended that over the years to Kubernetes. It also does infrastructure as code, like CloudFormation deployments. So that is effectively the pipeline management bit. In terms of how we do it in the sales world, we allow service owners to effectively declare their pipeline strategy so that they can say, I want to deploy to a given canary cluster, effectively run some metrics checks, do some soak testing, and then deploy to the rest in parallel. So that is the key part for us of allowing service owners to declare where they want to be deployed, how safely or how fast they want to roll out. We do have break glass mechanisms if they need to roll out a fast fix as well.
Thank you.
Okay, we've got time for one more question. Yes, great. Didn't have to walk far. So we're using multi-AZ EKS clusters, and we're using Spark in production as well recently. Carpenter made that fantastically easy with node selectors and stuff like that to opt in and opt out. Yeah. Just interested to know, we're using topology spread constraints for fault tolerance across the AZs. Just interested to know what your opinion is on that, between using that and the cell structure that you've got. Obviously, I know that's a relatively recent thing.
Yeah, that's the main thing. At the point we were doing this, topology spread constraints, I think were being discussed, but we're nowhere near actually ready to use. I think we would. There are definitely use cases where we could maybe go to a single multi-AZ cluster in a region and then still some single AZ ones. We quite like following the AWS effectively fault zones because it makes it easier for us to reason about if there's if we see problems or metrics diving in, say, 2 clusters, and those 2 clusters in the same AZ. It makes us really easy for us, even if AWS are currently saying no, there's no problem here. We can quite quickly go, we are seeing a problem in 2 clusters. They're only in a single AZ. We think there might be an issue. Could you please investigate?
Thank you. It's awesome to hear that you're using Carpenter as well. So definitely always want to hear about that. So yeah, come and grab me after. And we haven't talked about your journey with Carpenter yet because it's a future thing, but we've definitely had that discussion with Skyscanner as well. So it's cool stuff.
Okay, I've immediately broken the golden rule of not going over time, but thank you very much for a round of applause again.
Thank you.